Hello, everyone, and thank you. Hello, everyone. My name is Jimmy. I'm an engineering manager at TV2 Denmark. That's a broadcasting station, but I'm not working with TV because they also run a streaming service, which is where I put my work. And I'm here to talk to you about being cynical. And I'm not talking about people being cynical, but software being cynical. And much of this talk is inspired by a guy called Michael Nygaard, a book that he wrote called Release It. And there's one quote in his book that I would like to tell. Cynical software expects bad things to happen and is never surprised when they do. Cynical software doesn't even trust itself, so it puts up internal barriers to protect itself from failures. It refuses to get too intimate with other systems because it could get hurt. So that's what we're going to talk about. But let's first look at the law of large systems. Because if you run a small system, you probably don't have that many problems with it, and probably also don't have that many customers on it. But the larger a system becomes, the more and more components that the system is consisting of, the more and more things can go wrong. Because when there's like hundreds or thousands sometimes of, for example, microservices is a good example, running, there's always some piece of the software that's getting redeployed or reloading or actually have failed. So everything is normal is becoming, or everything is working is becoming the anomaly. It's actually more often that something is wrong than something is not wrong, because there's so many components involved. So everything is working is the weird state. So what can we do to contain the blast radius of something when something goes wrong? And how do we avoid these failures to propagate and crack through our microservice architecture? And one thing is, of course, stability. So let's talk about what stability is before we look into how things can go wrong. It's an architectural trait that tells if the system is available or not. So observed availability is the system is responding to requests that's coming into the system. That's the observed availability. And a fault is when some incorrect state is introduced into the system. A fault doesn't necessarily mean that it's visible to customers. It doesn't even mean that the system is not running normally. A fault can happen if you put up barriers without destroying your system. When a fault becomes observable, it's called a failure. So that's the inability of the system to actually do what it's supposed to do, and then becomes observable by the users. And no matter what we do, no matter how many safeguards we put up, and no matter how good we become, systems will always fail at some point. Faults will creep in, especially around the edges of systems, especially where you have integration points, like especially in distributed software, you have a lot of different integration points to other services, to databases, to what have you, caches and so on. And especially around there, that something usually goes wrong. And you can have component level stability without having system level stability. If you do a lot of tests on one service, it doesn't really mean that your system is fail-proof. For example, let's say we have two microservices. One is dependent on the other one to serve its responses. And in your dependent microservice, something goes wrong, a fault is triggered. And eventually, that thread pool of your dependency becomes full. It can no longer serve requests because it takes too long to actually get responses out of the system again. And at some point, it probably starts responding entirely. And in your service that's depending on the other one, if you not put up barriers to prevent this, these failures will start to crack through the system, and the architecture actually amplifies these faults. And then you as a caller starts to have problems. And at some point you probably start responding as well, and then you have loss of availability. because it's observable to the user, and you're no longer serving requests at all. So let's look at an example of this. For this, I created a small demo of, I work with video platforms, so I had to make a small demo of a video platform. It's very tiny, but it served the purpose. In this example, we have a user that talks to an API gateway. And that API gateway has two downstream services. One is content, that's regular video content that an editor put up, so that's quite static. Another one is a pseudo recommendation engine that I created. What it really does is just show you random data, but just to have something dynamically. And both of these services are getting their data from a Redis cache in this demo. So let's see what happens if the content API stops responding and you have not put up any barriers. This is an example of a request to that API gateway. It's in GraphQL. So I'm making a request to the editorial content. So that means that I'm making a request that's being forwarded to the content API. And right now it's working perfectly. I'm getting a static response back. But let's try to introduce some kind of failure into this system, simply by shutting down the content API. So we're stopping the Docker container that the content API is running in, and at some point when it's shut down, we'll see what happens. Yeah. We get a slow response, which means that our threads now take longer time to execute. And when you have many, like several hundred requests per second, these threads will start to queue up, and at some point your old thread pool will become full, and you will stop responding. And we see, probably to no surprise, that we get a connection error to that API. I'm just going to start it up again. So it's probably no surprise that when you not put anything in to prevent this, that a failure will happen. So we actually had system failure here. So what can we do to prevent this? You can design something called shock absorbers, and that can be directly in your software in some kind of middleware, or even in a web server or some other server. You can build these shock absorbers. And some of them, these are from Michael Nygaard's book. Some of them are, for example, fail fast. So the faster you can tell, the faster a dependency can tell you that I'm not serving requests, the faster you can release the thread and carry on with your regular work instead of piling up and eventually having thread contention. So fail fast is one shock absorber. Bulkheads is another one. For example, let's say you have two dependent on components. So instead of having one thread pool that you use to query or to call both of them, and one starts being slow, that means that all your threads will be busy waiting for that service, and that means that you will also not have free threads to talk to the other service. So one thing is bulkheads. So that means that you could, for example, have two separate thread pools. So bulkheads come from ships that, if you look at the ship, it has different compartments so that if water flows into one part of the ship, it doesn't sink always. Titanic had these as well, but it sank anyway. So that's the idea of bulkheads. Another one is circuit breakers, which we'll come back to. And of course, load shedding. That means that you as a server tells the caller that I'm busy, I cannot handle any more requests. So there you have the chance to redirect your request somewhere else. And of course, caches, because everything about availability is about giving a response as fast as possible, and caches are quite good at that. So we will try to stop propagating these faults and errors and prevent them from spreading. If we look at another example where we actually built in shock absorbers, the same scenario, some dependency you are dependent on starts or triggers some kind of fault, its thread pool becomes full, and it stops responding. But now you as a caller tolerates this behavior. The fault still happens in your dependency, but you're prepared for this. So instead of having loss of availability, you have loss of feature. So that dependency, that feature that dependency was responsible for, you will of course not have that one, but you can still carry on and serve requests, and you can continue in a degraded state instead. So you have loss of feature instead of loss of availability. And circuit breakers is one of the patterns that we use to handle this situation. It works basically like an old-fashioned circuit breaker that you would find in a house or something like that. That when the circuit is closed, everything is just going happily. You're sending requests out to a dependency without any problem. Whenever a failure whenever a failure happens, for example in an HTTP world, so that could say when you don't get a 200 or 400 range response code, you tick how many failures do you get from your dependency. And at some point, when you reach a threshold, you transition from closed state to open state. So it's basically a simple state machine. And when the circuit opens, you stop calling your dependency altogether. Because the last 5 times you called, I got a slow response. So it's hurting you, and it's probably also hurting your dependency, because if your dependency is down because it gets too many requests, it doesn't help that dependency if you just continue firing requests at it. It's like kicking a man already lying down. So it helps both parties. But what you can do instead of calling the dependency is that you go to some kind of implemented fallback, which could be call another service or take stale data from a cache or whatever your situation might be fitting for your situation. So in this case, you also get fast response because you're not going to your dependency and waiting for a timeout. You actually take something that you know will be there or has a higher probability of being there. Sometimes you need to go back into closed state and to self-heal in the system. So once in a while, when you have been sitting in open state for long enough, you go into half-open state. Is where sometimes you send a request out to a dependency to see if it's still not responding. And if it's still not responding, you just transition back to open state. But if the dependency is now starting to take requests again, you transition into closed state. So there you have both self-healing, you have fast responses, and you're helping you and your dependency recovering from this fault. So let's observe this behavior instead. It's the same architecture, except this time in the API gateway, I've implemented circuit breakers and actually also bulkheads because I separated the 2 thread pools. So one thread pool for content API, one thread pool for the recommendation API. So there's a circuit breaker in both of these cases. So let's see what happens now. So in this API call, we can see that I'm making a, can you see it? It's a bit blurry. Can try making it better. So in this case, I'm making both a request to the recommendation API and the editorial API. And I added a few extra fields to this one. One is circuit breaker open? So that means, are we in, let me see. Are we in the open state? Is response from fallback? That means that are we actually using the fallback method instead of the response we got from our dependency? And the last one is response short-circuited? Because you can get a fallback without having a short-circuited circuit breaker. And we can see that now everything says false, 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 which means that we are actually in closed state. And we can see that we are getting random responses from our recommendation API by the description changing every time I make a request. So let's introduce a failure into the recommendation API this time, simply by stopping the Docker container. It's still running. Should be there. Now we get a slow response, and we see that the circuit breaker is still not in open state, but we actually got a response from the fallback, and it's not short-circuited. If we do a request again, we can see that we are again waiting for the timeout, and we have the same situation. We are still in open state, we get a response from the fallback, and the circuit is not open. So what I've done in this scenario, so my fallback that I implemented was, instead of, when I'm requesting recommendation API, if I get an error, I will request the content API instead. So therefore, in this case, we will actually see that the response from the editorial content API is exactly the same as in the recommendation API. And it could be any implementation that you can imagine, and that's fitting for your system as a fallback. And the reason why I cannot trigger an open state is because I'm not making requests fast enough, because it has this window where it looks for, it needs that many errors within a time window before it actually opens the circuit. So we can put some load on it, and making sure that I'm using the right port. I am. So I'm using a load testing tool to put some load on the system, and that should force it into, see, it's already now in an open state. So this means that the circuit is now open. I am receiving responses from my callback, and we are short-circuited. But one thing that you will see now that you didn't see before is that we get extremely fast responses, because now the circuit is open, so we are not even trying to get a response from the recommendation API. We are not even calling it. We are going directly into our fallback. And at some point, if I kept refreshing, I would see sometimes that this one would turn into false. That's when it transitions to half-open state to try and send a request out to the dependency to find out if it's recovered or not. And if we look at our load test that I've started, this is the HTTP code that we receive. We see at no point, you cannot see anything at all. At no point are we getting anything else than 200 OK. So even though we have a system that's down, we are in a degraded state, but we're still serving requests, we're still serving customers. I'm just gonna recover my system. Yeah. Now it should be back to normal. Yeah. So that in this case, we can see that our shock absorber actually does what it's supposed to do. So how can we test this? We can, of course, do some a bit more scientific approach by creating some quality attribute scenarios that tells you, in these scenarios, in this time frame, we need to have this thing happen. We could do load tests like I did. We could also do manual tests, which I also did now. But I really want this to be automated, and I want this to run like a test scenario in my CI pipeline, so I don't rely on people remembering to do these tests. We could, for example, start up all our environment and run some integration tests or system tests on the API gateway and introduce some kind of errors into the systems. And for example, like using Docker, like I just did, I'm running all of this system in Docker right now, and it's not a big problem. So that's one thing that we could do. But what if your microservice architecture looks like this? You cannot spin up hundreds of or thousands of microservices every time you want to run some kind of test. It will take hours and probably take a lot of CPU and resources. So it's not really feasible to start up your entire environment every time you want to test the stability of it. So let's look at some approaches that we could do. This is how I imagine or how I see most distributed software is layered. It has some kind of resource that is some kind of endpoints that the service exposes. It has some kind of service layer. It has some kind of domain logic. It has repositories and data mappers to databases and so on. And it has some kind of HTTP implementation to dependent on component. So in this case we looked at before, this one was our API gateway, and this one was the dependent on either the what's it called, the content API or the recommendation API. So that's how it could look. One thing that we could do to test it was to create test doubles instead. So we could, for example, use an in-memory database if we have a database. Or we could create a test double. Can you see? Yeah, it's a bit. This one I'm highlighting is the HTTP client, so the piece of your code that makes the HTTP calls from within your service. We could create a test double of that and simply just simulate that we are doing HTTP requests. But it won't really happen. You will never call out of your service in this case. There are several, we have done this and still do to some extent, but it's not really, it's more a unit test thing in my opinion than an integration test. Because it's more difficult for you to actually test the failure scenarios that could happen over a network, or error responses that could come from a dependency. Another thing is that if code coverage is important to you, you will have zero code coverage in your real implementation of the HTTP client. So what we are doing at TV2 and what I'm proposing that we do instead is that we move one step out. So instead of creating a test double for the HTTP client, we actually do a test double of the dependency. So we create a test double of the content API and the recommendation API instead, or any implementation that you might have in your system. In this way, you will actually get to have code coverage in your HTTP implementation inside your microservice, but you will also introduce all the different failures that can happen over the network, like latency, wrong responses, and things like this that could happen from a dependency. And to do this, we use a tool called Montebank. It's a multi-protocol test double over the wire. So it's actually a system that's meant to replace real dependencies that you can manipulate and really do some different kinds of tests over the network. So one of the neat things that Montebank can do is that it has an implementation of a proxy. Their test doubles are called imposters, so you can create a proxy imposter. So let's say that the system under test is our API gateway, and the dependencies are our content API and recommendation API. So in between, we put up a Montebank proxy imposter. And what this will do is that instead of calling out to the dependency, you actually call out to the Montebank imposter instead, or the test double instead. And then it will forward the request to the real service and record the response. So the next time you call the service, you won't get a response from the dependency, you will just get the canned response from Montebank. So it's a record and replay situation. And Montebank is just, of course, one of the frameworks that can do this. The Pact is a good one as well, or Mock, what's it called? Mock server is another very used one. But now you have an actual recording of how your dependency actually will behave, or how it will respond. Montebank is configured using some configuration in JSON, and this is how an imposter could look. You specify some kind of port. It actually starts up a web server on that port with that canned response. I'm telling that it should be HTTP protocol. And then I'm defining an array of stubs. And we can see that I'm creating a proxy. So whenever Montebank receives a request, I'm telling it to forward the request to the recommendation API, and also record the method, the path, and the query parameters that I sent along with it. So now that I've actually created a test harness, instead of having to spin up all my system to do this test, I can start up my system on the test, or my unit on the test, and my immediate dependencies. So I only have to create a test double and start up the content API, test double, and the recommendation API, test double, along with, of course, the system that I'm testing. So now my implementation looks like this. I have, as I told you, 2 thread pools, so I have 2 different HTTP clients, and I have 2 test doubles, a Montebank stub of the content API and a Montebank stub of the recommendation API. So let's take a look at how this could look. I have the last example here. So right now, I'm actually not talking to the 2 APIs. Now I'm talking to Montebank stubs instead. And the behavior is like it is before. We still have implemented circuit breakers and things like this. But now we can actually start introducing different scenarios. Montebank, as I told, is configured using JSON. This one I cannot enlarge. Doesn't really help. Does it? A little bit. So I created a test double for the recommendation API. Actually, I created 5 different responses. So I'm requesting recommendation API with a limit of 1. So if we find this one, it's a GET request to path recommendations with limit 1. So that's the first predicate. The way Montebank works is that it has predicates, and whenever that predicate is fulfilled, you'll get the response from that recording, or from that belongs to this predicate. So this is the response that we recorded and that we will send back. And it says Danish comedy show, and that's the response that we can try changing the year to 19 instead, and post that, or put this. It should change the response, it does. So we can see that now we get another description. We can also introduce different kind of behaviors. For example, wait time, or what they call wait time, which is really just how long time do I wait before I give a response as the Montebank stub. So we can try setting this up to 2,300 milliseconds instead, which should be enough to trigger the circuit breaker, because I set a timeout of 1,000 milliseconds. And we can see that it takes longer to do the request, which means that I'm hitting a timeout. And we can also see that circuit is not open again because I'm not doing request fast enough, but we are getting a fallback, which is the same fallback as before. Instead of getting a request from the recommendation API, I get a request from the content API. But now we have a way to actually control this in a test harness. So now we're in a controlled environment. We can try putting some, if I just change the port on my load test. And do the load test again. We should see, yeah, now we get enough requests that we are actually hitting the open state. We are still getting only 200 OK. So what happens if I put this one back at 300 millisecond response? It should, yeah, now we are back in closed state. So we hit a window where the circuit breaker would go into half open state and found out that the service is actually responding now. So it went back into closed state. And we can continue playing around with this. Now we're introducing some wait time again. And we can see that we went into open state again. And if we look at our test, how it's running, even though we are just failing a dependent on component, we are still only getting 200 OK, which means that our circuit breaker is working as it's expected. It's not, the system is still available. It's not a loss of availability. It's a loss of a feature that I'm failing. But the system is running. I'm gonna put this one back. So now we created a test harness, a control environment where we can introduce these experiments and see how our system behaves under these extreme circumstances. And we are making calls over the wire. Now we have an opportunity to automate this because we can configure Montebank, which means that I can now run these. I have an opportunity to run these in my CI pipeline, just as you would at a regular unit test. So before we go to the last part, let's look at some code. Just a moment. It's already here. Is it enough? No. Let's give it a bit more. There. Yeah. So I created some automated tests using a framework called Spock. And I'm using another project called Testcontainers to start up the Montebank stops whenever my test starts. So whenever my test starts, Testcontainers would spin up my test, and automatically when the tests are done, it will clean out the Docker containers again. If you're in the JVM world and working on Docker containers, I highly recommend trying out Testcontainers. And Spock, of course, as a test framework. But anyway, the first test I did is just a regular success test that whenever we query for an ID with a limit of 1, we actually get 1 content back. So I have my GraphQL query here. I'm sending a query to the editorial content with limit 1, and I'm asking for ID. I'm sending the post request to the Montebank stop. I'm reading the content, I'm making sure there is 1 in the return statement, and I'm making sure that the ID field is there and it has a specific ID in the return. I'm doing a bit more advanced test with 3 different, with a limit of 3, which means that I will get 3 results back, looping through them. But the most interesting ones are actually the 2 last tests that I make. When receiving a timeout, Hystrix or the circuit breaker returns a fallback content object instead. So when I do a call to the editorial content with a limit of 4, I ask for ID and is response from fallback. And then my test is that give me the first element that is returned, find out if the ID is this specific 123-fallback, and I'm also making sure that the flag is fallback, is response from fallback true. So that's the one we saw in the, if I can find my browser, is response from fallback. This is this one I'm listening on from the return statement of the server. And the last one, I'm introducing a test double that instead of returning application JSON, it returns text.plain. And that's what I meant about now you have the control, because not only are you able to test what happens if I get a slow response, I can also test what happens if I get gibberish from my dependency. And in this case, text.plain is gibberish because I'm expecting JSON. We can try and run these. You can see that Montebank, that our Docker containers are started up. Our tests are being run. You can see those out here. They're all green. And they all succeeded. The reason why this is possible is because I'm using this test double or Montebank as my test double, and I can configure it. So if I look at the configuration, so this is the configuration file that I'm using to prepare my test doubles. One is that whenever I basically use the limit to as a predicate to decide what responses I should get from the test double. And the ones that are introducing failures are the limit 4. You see on limit 4, I added a wait time of 10,000 milliseconds, which means that whenever a request is sent, a GET request is sent to the /content with limit 4, I get a response, but it also waits 10,000 milliseconds. And if we go back to our tests, this is exactly what we're doing here. I'm calling content with a limit at 4, and I'm getting the fallback. So now we're actually able to run this automatically and create our tests just as we are used to using automation. So now we have a way of actually getting confidence that we introduce some kind of cynicalism into our software. We can be sure that the software behaves or monitor how the software behaves under different controllable circumstances. And if you are into distributed software and breaking things and testing, I highly recommend reading the book by Michael Nygaard, Release It. And then when you do software, think destructive and be especially careful around integration points and think what can go wrong here. And of course, handle exceptions and really test your resilience of your software. That's it. Any questions?
Are there any questions?
Hmm?
Oh. Sorry.
So I have a couple of questions. For example, when you test your service, where you exchange the dependency for a fake one, do you then actually mutate the database based on the request from the fake?
So let me just put up one of these. So kind kind of, but I'm not concerned about the database. If we look at this is the system that I'm testing, and in the wire here, I put up this proxy imposter. So instead of requesting the recommendation API, I'm requesting the imposter or the test double, which will forward the request to the real service. This service, however that gets its data, I'm not concerned about. In this case, it actually gets its data from a database, but it could be anywhere. You're not concerned about that. You're only concerned about your immediate dependency.
Okay, but couldn't you have a service that does something, like writes something to the database that is based on the request gotten from the fake service? So like if there's kind of a data dependency between those two. So you mean that, for example, say you send a post request to a downstream to a dependency, and you want to test if that mutation actually had an effect? No, more like if you like do maybe some caching in your own service or something in the database, and you like based on the request to your dependency, and then you cache the response from the fake dependency or something like that. So yeah.
I don't think I've experienced that case, and so what I'm thinking that you're saying is that the mutation you did on your dependency, you want to have the result or somehow know the result of that mutation and use that in another place in your application or in another test. Is that the case?
No, it's more like, okay, you are the service that you test, and you have the database, and then if the database you have, actually the data in it is dependent on the response you get from your this other service you depend on, which you can switch out with as a testing.
So if the API gateway had a database, and you send some kind of request to a dependency, and the response has some kind of dependency to the data in that database, or has some kind of relation or something like that.
The database should have. The database depends on the response from the dependency.
It's not a case that I'm sure you could find a way around it. I think architecturally there's maybe a problem if you are in this case. Because as Montebank is good for stopping either TCP or HTTP or SMTP, but databases it cannot really stop. So there are other systems that can do this. For example, in-memory database where you bootstrap your database with predefined test data, and there you can make sure that your test data is related or correlated to the rest of your test harness.
And then I'll try to make it quick. The second question, the last question. When you have the circuit breaker, don't you actually want to monitor it pretty much, because it's like the small like the fine tuning of it must be also really important. So let's say the time between requests when you're half open, you would need to want to really like fine tune that, because or for example how when you're actually full open, let's say you can like send requests like 500 like a second to some service, and that service can only handle 2 in a second, and then it's like all the time you send 500, and the circuit breaker opens, and it's like you have made a big queue of requests inside it, and it's kind of like it goes back and forth between these two states where it's like really halting the performance.
And that could happen. When my experience with circuit breakers, I've worked most with the Hystrix, which is being replaced by for example, Resilient4j instead. But my experience is that you really need to do some different kinds of load test when you've implemented your circuit breaker to fine tune it. What's the right timeouts? What's the right queue sizes and things like this before you actually are ready to put it in production. And I know with Hystrix and also a lot of other implementations, with Hystrix it sends out a stream of data, of how many requests am I getting, which state am I in real time. And History has the History dashboard, so for every circuit breaker you implemented, you get a small dashboard with how many requests how many active threads am I using out of my thread pool and things like that. So you get real-time monitoring. And that combined with doing some load tests or real-time load tests before you put it in production is really valuable, and you need to do that to get it right.
Anyone else? Okay, then thank you again.